Hello everyone to another problem solving session. Myself Maushandra, and this is week 4 of the for the session. We are still discussing the material balance problems. So every week we are meeting like this from 3 to 5 p.m. And also a brief introduction about myself. I'm a PhD scholar in the Department of Chemical Engineering, and the recording and everything is available in my YouTube channel. The notes are also made available to you. Are you able to access the recording and notes for the past 3 weeks?
Yes,
Yeah. Okay, great.
I didn't check the notes, but I checked the videos.
The notes are also available, like the questions basically, they are also available. If you just check your login in SOAM portal, you'll be able to find it. Okay. So let's begin with some questions on again material balance with reactions, and then I'll briefly discuss about recycle, some questions on recycle as well. Right, so this is the first question. I'll give you a few minutes, have a read. All right, then we'll begin. All right, done. So the this is the question that is in front of you. There's a reaction given for the production of acrylonitrile. So this is the product C3H3N, and this is polypropylene is the reactant, ammonia and oxygen. These are three reactants. So there is a feed that contains 10 mole percent polypropylene, 12 mole percent ammonia, and 78 mole percent of air. All right. So there will be percent, not one. All right. And we are told that a fractional conversion of 30% of the limiting reactant is achieved. So we have to later on understand what is the limiting reactant here. So take 100 mole of feed as basis. So we are told that just take 100 mole basis. First determine which is the limiting reactant. So A that we have to determine is the limiting reactant. Then we have to determine the percentage by which each of the other reactants is in excess. So there are three reactants. So we have to find the percentage excess for reactant. If one is limiting, then the other two will be the excess. So we have to find out what is the percentage excess for the other two reactants, and the molar amounts of all the product gas constituents for a 30% conversion of limiting reactant. All right. So we have to find the yeah, their product is acetonitrile. So you have to find number of moles for this and water in product, right? So there can be other constituents as well. So if some reactants that are unreacted, that will also come out. So these are some, but we will later investigate what are the other components in the product. All right. And whatever the components of the products, we have to find the molar amounts. So number of moles. So let's start. So we can try to make a diagram first in order to model a flow chart basically in order to model the process. So if this is the reactor, right? So what are the things that are entering? So take a basis of 100 mole. So feed 100 mole of feed. Yes. So your feed contains 10 mole percent polypropylene. So C3H6 is your polypropylene. It is 10 mole percent. So 0.1, all right. Then ammonia is 12 mole percent, 0.12. Then air is also entering. It was 78 mole percent. So it is 0.78. Okay. And what is coming out? So definitely the reaction products, which was acetonitrile C3H3N, then water. So these two will come out and the reactants will also come out. So since it is saying that 30% of the limiting reactant is coming out, so even the limiting reactant is not going to get consumed. So in this question, it seems likely that some components of all the reactants will come out. Okay. And also note air will have two components in it, oxygen and N2. Oxygen will be 21%, N2 will be 79%. Okay. So that we will individually how much it is there, we will calculate in a minute. So first let me complete this flow diagram. O2, N2, so these are the air components, number of moles for the air components of it is O2 and N2. Then propylene will also come out and ammonia will also come out. So in total, you see 6 species will come out in the product gas. Later on, that is the third part, we have to calculate the molar composition of each, like means number of moles of each of the components. So first we have to understand what is the limiting reactant. Okay. This pencil is doing something. What is the limiting reactant? So in feed, what we observe, so we have done this previously. So if you have understood how to do it, you continue doing it in your own notebook and we will later on match the answers. So please do it on your own, okay, if you understand how to do it. So in feed, let's find the ratio of number of moles of C3H6 in feed or in. I'm adding a subscript in in order to indicate that this is the number of moles of propylene coming or entering. So what is it? It will be 0.1 into 100, that is 10 mole is coming in. the number of moles of ammonia is similarly 12. Then what is the number of moles of oxygen that is coming in? So you know 0.78 or 78 into 100, so it will come out to be 78. Of this, 21% is air, so 0.21. Okay, so if we complete this calculation, what you will get? You will get 16.38 or 16.4 moles. So these are the first individual number of moles in the feed. Let's get the ratios. So ratio of ammonia to propylene. You can take other way as well in. So ammonia is 12 moles, propylene is 10, right? So it is 12 by 10. So it is 1.2. Similarly, ratio of oxygen, number of moles of oxygen by propylene in feed is 16.4 by 10. So it is 1.64. But if you see the reaction, what is the reaction? Let me write it. It is C3H6 plus NH3 plus 3 by 2 O2 gives C3H3N plus 3H2O. Okay, this is the reaction. So from this reaction, what is the stoichiometric ratios? Similar ratios. So let's calculate that. Number of moles ammonia by number of moles of propylene. I'm adding a subscript of stoich like this in order to differentiate these two ratios. So what we get, 1:1, that is 1. And similarly, number of moles of O2 by number of moles of C3H6 stoich. So this is 3 by 2 by 1. So it is 1.1. Now, if you compare the ratios that we got first, if you look at this ratio first and this one, what you see, one is higher in the feed, the number of moles of ammonia is higher, right? Means ammonia and then the required. So this means what can you conclude from ratio and the stoichiometric ratio, what can you conclude from this? Which is in excess? Which reactant is excess? Are you there?
Yes.
Yeah. So tell me the ratio that I calculated for the number of moles in feed, this one, the top one, and for the stoichiometric ratio, from this, what can you conclude? Which reactant is in excess?
Oxygen.
There is no oxygen in this one and this one. There is no
Sorry.
oxygen. Which two reactants are there in this two?
Ammonia and that
Propylene.
C2H6.
Yes. So which is in excess? Which is ammonia in excess or propylene is in excess?
Ammonia.
Ammonia, right. That is the answer. So we can understand that ammonia is in excess in the feed, all right? Similarly, for the other two ratios that we got with respect to oxygen, what can you conclude? Which reactant is in excess, oxygen or propylene?
Oxygen.
Yes. So if these two are in excess, this means what? Propylene
The
is the
propylene is the limiting
limiting
agent.
reactant. Yes, correct. All right. So part A is done. Then we have to find the percentage by which each of the reactant, means ammonia and oxygen, are in excess. So you have to find the percentage. So it is uh, first we have to calculate how much amount it should be according to stoichiometry, and then we already know the amounts of ammonia and oxygen in the feed, and then we can calculate the percentage excess. So according to stoichiometry, how much ammonia should be there with respect to your propylene. So it should be 1:1, right? With respect to propylene, ammonia should be 1, right? And how much propylene is there with us in the feed? It is 10 moles. So stoichiometrically, we need only 10 moles of ammonia, okay, for the reaction to complete. Similarly, for oxygen, the ratio, stoichiometric ratio tells us that we need 1.5 or 3/2. And how much, again, propylene is there is 10 moles. So we need only 15 moles of oxygen stoichiometrically. Now let's calculate the excess, percentage excess for ammonia. So it will be number of moles in the feed minus number of moles required as per stoichiometry divided by number of moles required as per stoichiometry. So in the feed, we are given 12 moles. We need stoichiometrically 10 moles. And yes, there will be 100%. So we need 20% of, or there is 20% excess ammonia there. All right. Similarly, oxygen in the feed, how much is there? Minus all right. This expression looks pretty much same, right? There is no change in it. So in how much oxygen is coming in? 16.4 moles minus 15 moles we needed for stoichiometric proportion to maintain stoichiometric proportion 200. So if you calculate this, what you will get? All right. So you will get 9.3%. Okay. Is it clear?
Yes.
Hmm? All right. Now we have to do, this is part B is done. Now we have to calculate the molar amounts of the product gas constituents for 30% conversion of the limiting reactant. So we are told that 30% of the limiting reactant is converted and rest 70% is unreacted. All right. So in the product, or see. So if we see how much of the limiting reactant is coming out in the product, out, number of moles of polypropylene in the product. I'm writing superscript out in order to denote this. It is 70% of whatever is coming in. So we know that, right? We know this value. So it is how much? It is 10 moles. Okay. So in the product, there will be 7 moles of polypropylene. Now, we have to also understand for the other constituents, right? So how will we do that? So before I start explaining it, how we do that, let me talk about quickly about this expression, which involves a parameter that is called extent of reaction, represented by xi. This is called extent of reaction. And it basically tells us about how much of moles is getting reacted. So that is why it is the unit of this particular quantity is moles. So there is a very easy expression that you can remember later as well. So for number of moles of species I that is coming out is equals to number of moles of species I coming in. So not, I'm representing with not sign, plus nu I. Nu I is the stoichiometric coefficient of this species in the reaction into your extent of reaction. All right. So this is a very important expression to remember. So here Ni is the number of moles of species, any species I. Ni naught is the species that is coming in. Nu I is the stoichiometric coefficient, and psi is the extent of reaction. So the units, if you see, moles, moles, and this is for extent of reaction, the unit is also moles. Now for stoichiometric coefficient, when you write it, for reactants, it is negative, and for products, it will be positive. So for the reaction that we are given, for that reaction, again, let me rewrite the reaction. It is C3H6 plus ammonia plus 3 by 2 O2 gives C3H3N. It is the acetonitrile product plus 3H2O. This is the complete reaction. For each of the components, we can write this expression. How shall we write it? So for species, first species, let's write it for first species. Although we already calculated it, but we can still do it. So for C3H6 that is coming out, is equals to number of moles of C3H6 in. Now the stoichiometric coefficient will be -1. All right. The stoichiometric coefficient is 1, but since it is a reactant, so we have to add a minus sign here, and extent of reaction. So each reaction will have its own extent of reaction value. All right. Xi will be different for different reactions. So this is the expression that we have. All right. So we already calculated number of moles of polypropylene that is coming out. Right. This is 7 moles. This is 7 moles. So we can write this 7. And how much is entering? 10 moles is entering minus xi. So xi will be 3 moles. All right. Now we can use this xi value to write expressions for each of the species in the reaction, and uh, basically calculate the molar amounts of each of the species. All right. So let's do that. So for ammonia, stoichiometric coefficient will be -1, and we already calculated extent of reaction, it was 3. Okay, so you know how much ammonia is coming in the feed. So it was 12 moles, 12 minus 3, so 9 moles of ammonia is coming out. Then for oxygen, similarly, you have to write this expression. If there is any doubt, all right, let me know. I'll be like happy to explain things again. Minus 3 by 2 into 3. So oxygen that was coming in was 16.4. Okay. So if you solve this 16.4 minus 4.5, so it will be 11.9 moles. Okay. Similarly, for acetonitrile, your stoichiometric coefficient will be +1 since it is in the product side, and your extent of reaction is 3. Now please note, in the feed, we didn't add any acetonitrile. So this term will be 0. So out, how much polypropylene that you will get is basically 3 moles now. Okay. Then water is another constituent. Okay. So do we know how much water is coming in? If you read the question carefully, there is no water coming in. So here also the first term will be 0, and it will be the water that is coming out only is because of the reaction, so it will be 9 moles. And then nitrogen, last component is nitrogen. So it was part of the air, right? It was part of air. So since it is inert in nature, it is not participating in the reaction. So however much N2 came is same as how N2 going out. So we will basically apply the fact that 79% of the air is N2. So 78 moles, or for 78 moles of air in the feed, 79% is N2. Okay. So this is how I wrote this particular expression. So if you do that, if you solve this, you will get 61.6. Okay. So there you go.
Yeah.
This is the complete composition of the product gas. Then one new thing that you learned in this particular question is this expression. All right, this is very important. Please note it down. All right, it will help you in different types of chemical reaction based questions. All right, whether the question involves one reaction, two reactions, or however much, you can use this particular expression in order to solve problems. Okay, any doubt in this particular question?
No.
No, right? Okay. Now moving on with this one. So this is a very simple question. You have to calculate. I guess you left the meeting momentarily. It's fine. So this is the second question. I'll give you a few minutes. Read it. Means it's a very simple question. Can you excuse me for 2 minutes? I'll just come back, all right, in 2 minutes. While try reading this question, and if you understand it, start solving. I'll come in 2 minutes. Okay.
Okay.
Okay, I'm back. So this question talks about there's a gas, all right, and the composition of the gas is given. 40% is N2, 20% CO2, and 20% O2, and the rest of it is water. Okay, so how much water is there? If you take 100 moles, all right, as a basis, then you will see that N2 will be 40 moles, CO2 will be 20 moles, and O2 is 20 moles. So water is 60 plus 20, 80. So water is 20 moles. Okay. Now you have to calculate the composition of this gas on a dry basis. So dry basis means you have to neglect water. So then in that case, you will take, or you will calculate the amount of N2 out of total of 80 moles only, not 100 moles, because 20 mole was water, right? We have to remove that. So now in that dry air with zero water, N2 will be basically 40 by 80 moles. So mole by mole, right? 0.2, 1 by 2 means 0.5, sorry, 0.5 mole by mole N2. CO2 will be 20 by 80, 1 by 4, right? That is 0.25 mole by mole. Next, for O2, similarly, 20 by 80, 0.25 mole by mole. All right. Is it understood? This part
Yeah.
is understood? Yeah. Okay. So that's it. We had to do this only. The question is complete. Uh, let's move to the next question. So this was the question that we couldn't discuss last Saturday, right? So I wanted to do the first question based on the question that we discussed today first, all right? So in this question also we will use the concept of extent of reaction in order to solve this. As you can see in part A and part B, they're asking the extent of reaction. So I'll give you a few minutes, start reading it, okay? And after that, I'll start solving. So let's begin. So there are two reactions here, all right? Reaction 1 and reaction 2. The reaction 1 is basically the formation of formaldehyde from methanol. So formation of formaldehyde from methanol, this is reaction 1. Whereas what happens in reaction 2 is some of the formaldehyde that is formed in reaction 1, it is getting reacted with oxygen to produce carbon monoxide and water. Okay. Now there is an assumption, assumption that whatever methanol, and we are giving twice the stoichiometric amount of air. All right. So these two things are entering. It will lead to complete conversion of methanol to the desired products in reaction 1. Okay. So what this means, this statement indicates that your methanol is the limiting reactant. Because why it is the limiting reactant? Let me explain again. So this assumption talks that the methanol and the twice the amount of air. So if you see reaction 1, there are two components, oxygen that is coming from air and the methanol. We are giving double the amount of air that is required stoichiometrically, and methanol is like, so stoichiometrically it is that much only, 1 mole, let's say. And it is, these two components leads to complete reaction completion. All right. So when we talk about the reaction is completing, leading to complete usage of the reactants, this would mean that the methanol is getting reacted completely, but the air will still remain. So the how much product will be formed will be governed by how much of the methanol is there in the reaction. So this argument helps you understand that methanol is the limiting reactant, all right, in reaction 1, and it will drive the reaction 1. Also assume that 90% of the methanol results, 90% of the conversion of the methanol results, all right, and a 75% yield of formaldehyde occurs based on the theoretical production of formaldehyde by reaction 1. So based on these assumptions, answer these following questions. Okay. So before we start solving part 1, let's take a basis of 1 gram mole of feed. Okay. Let's take arbitrary basis of 1 so that we can do the calculations further much more easily. Let's take a basis of this. Let extent of reaction R1 be xy1. Okay. So if we now apply the equation that we saw previously, so this was the equation that we saw. If we apply this particular expression for the species methanol, what we get that is coming out is equals to methanol that is going in stoichiometric coefficient 1 xy1. Okay, so this is the expression. Now what we understand, there is 90% conversion of methanol. So fractional conversion F for methanol is 0.9. That means methanol that is unreacted is going to come out. 1 minus F is 0.1. All right. So we took a molar basis. We took a basis of 1 gram mole, right? So we can now calculate how much of the methanol is coming out, because we know zero point 0.1 uh, of the methanol, or 10% of the methanol is going to come out, and the feed amount, total feed, is 1 gram mole. So 0.1 into 1, right? So we'll get 0 0.1 moles that is coming out. How much is going in? How much is going in is 1, right? Here is 1. So extent of reaction for reaction 1 will be what? 1 minus 0.1 is 0.9 moles. This part understood? This is part A. Understood? Any doubts? Hmm?
No, no.
Oh, okay. So this part 1 is complete. Now for part B, we have to calculate the extent of reaction in for reaction 2. This is done. For part B, we have to calculate the extent of reaction in R2 for reaction 2. So B. Now let Xi2 be the reaction of R2. Now if you see R2 reaction, this is the R2 reaction. There is formaldehyde, oxygen, these are the reactants, and carbon monoxide and water is coming out. So we can write a similar equation for the species formaldehyde. Okay, if we write it, let's write it first. I'm sorry, my pencil is misbehaving a lot today. Okay, so this is the expression. Now what we see is we don't know either, like how much is coming out and how much is coming in, for how much moles of formaldehyde is coming in and how much moles of formaldehyde is coming out. All right, in this particular expression, this we wrote for reaction 2. Similarly, if we write this expression, write a similar expression for formaldehyde for reaction 1, how much it how much how would it look like? Now, this is for R1, or reaction 1. In reaction 1, we are not adding any formaldehyde. So this part will be 0, right? And we already know the extent of reaction for reaction 1. So for R1 will be equals to xi1, which was 0.9. Now also note that in reaction 2, the formaldehyde, which is the reactant there, where it is coming from? It is coming from reaction 1, right? So in that, if we apply that logic, the number of moles of formaldehyde that is going in reaction 2 is also 0.9 moles. Okay, so if we fit this value for this particular expression, what we get, okay, so we still have to calculate xi2. uh, Now let's use the fact that the yield is given to us, yield of formaldehyde is given to us. It is 75% or 0.75. What is the definition of yield? It is a ratio of moles of desired product by moles of reactants entering the feed, okay, or entering. So the desired product is your formaldehyde, okay, and we already know how much from this expression R1. Let's write it as R2 for clarity. R1, R1. Okay. So total yield of the product formaldehyde for R2 by how much moles of reactant is entering. So if you see overall, it is the methanol that is entering. It was 1 gram mole, right? And it is so we see there is an expression here that will help us calculate xi2. So how much it will be? 0.9 minus 0.75 will be 0.15 moles. Okay, is it clear how we calculated xi2 or extent of reaction for reaction 2?
Yeah.
Yeah. Okay. Now we have to tell how many. So let me add another page. Part B is done. Now in part C, we have to tell how many number of species are there. or how many number of species material balance you can write. So it's like you don't have to do anything. You just have to look at the expression that we are given, sorry, equations that we are given for reactions. So if you see, there are how many uh, reactants and products overall? So there is
Six.
one methanol, yes, two, three, four, okay, then five, five, and there is one more hidden uh, species which is not reacting. It is an inert species, that is N2, 6. So there are 6 species. Okay. Now C is done. D. We have to calculate the exit stream composition of methanol, then for O2, N2, formaldehyde, H2O, and CO. So we will do this together. Okay. C D to I. Okay, we will calculate this together. So for that, let's write what is the total number of moles that is coming out in the product. Let's calculate that first. Total number of moles exiting. So let's denote it with P. So P is equals to number of moles of all the species that were entering. So there were how many species? 6 species. So number of moles, summation of total moles that is entering 6 for 6 species plus for these 6 species the stoichiometric coefficients, and there are 2 reactions. So extent of reactions will be also have to be included. So this is like the summation expression, all right? Okay. So this is term 1, and if we divide it, so this will be term 2. Let's say this is term 2. Okay, term 1 and term 2. Let's first calculate term 1. So what you see, how many things are entering into the reaction, into the feed? First thing that is entering is the methanol, right? And another component that is entering is your air. Methanol entering, that we already know, it is 1 gram mole, we have assumed it, but we have to calculate how much moles of air is entering. So how shall we do that? We know stoichiometrically how much oxygen is entering, right? And we are giving twice the amount of oxygen that is required. So we will use that information to calculate oxygen entering. So we are giving twice the amount of stoichiometrically, 2 into stoichiometrically amount of oxygen required. So we require, according to the reaction, only half moles. And the total feed F that we considered, or 1 gram mole that we considered. Okay. So from this, what we see, it is only 1 mole of oxygen that is entering. And again, we know that in the air, 21% is oxygen, right? So this will, so 21% is oxygen, and we know 1 mole is the oxygen in total air. The total number of moles of air will be 1 by 0.21. Okay, so it will be 4.76 moles. Okay, and similarly, how much is N2? Nitrogen. How much is the nitrogen? It is 79% of the air. So it will be 79.79 into 4.67. 3.6 3.68, but it is not matching the answer that I have done. Why? Mm, sorry. Yeah, we can do it like this. Mm, the total number of moles of N2 will be 4.67. All right, is the airs minus 1, the oxygen, right? So it will be 3.76 moles. Okay, there you go. So the term 1 in this particular expression will be then 1 plus, because we know 1 gram mole is methanol plus air, so it is 4.76, that is 5.76 moles. Term 1 is solved. Okay, now for term 2, if we expand it, all right, um, let's expand it for each of these components. So there are 6 species. So difficult to write today with this pencil. It's making me cry. Honestly, this pencil is not working well. So I'll do shortcut, okay? I feel very lazy to write everything. I'll do a shortcut. So if you see the expressions for the reactions that are given. So for methanol, it will be -1, oxygen it will be -half, the stoichiometric coefficients. Then for formaldehyde, it will be 1, water, it will be 1, all right? So these are the stoichiometric coefficients. And for reaction 1, so extent of reaction 1, it was 0.9, if I remember correctly, plus 0.9 into the stoichiometric coefficients of all the reactants on the products. It will be -1 minus half plus 1 plus 1. All right. And there is like n2 as well, but for that it will be 0 because it is not getting involved. And there is CO as well in the species, total number of species. For that as well, the stoichiometric coefficient will be 0. Plus, for reaction 2, the extent of reaction was 0.15. And similarly, the stoichiometric coefficients for reaction 2 will be, for methanol, it will be 1, minus 1. Oxygen, it will be minus half. For CO, it will be 1. Water, it will be 1. For N2, it will be 0. And for methanol, it will be 0. Okay. So let's write it quickly. Minus 1. Minus 1. Minus half. Plus 1. Plus 1. And for methanol, it will be 0. And for nitrogen, it will be 0. So if you quickly solve it, means do the arithmetic thing, what you will get? 0.9 into, if you are doing it, please let me know the answer, right? My pencil is not cooperating with me today. Mine, it will be half. And for this, it will be half. Point 0.45 plus 0.075. Okay. And this is the part 2, right? So if we do addition, 0.525. So if we add now part A and part B, it will be 5.76 plus 0.525. So it should be 6.195. So you can write it as 6.2. All right, 6.2. Is it all right? Did you also get the same answer? Hmm?
Yeah, okay.
Yeah, okay. Okay. Now, we now found the total number of moles in the exit stream. So we have to calculate the percentages. So for that, we have to calculate the ratio of number of moles of individual ratios of number of moles of say methanol divided by the total into 100. Okay, so let's do it one by one. If we see for methanol, give me a second, okay? Let me reshare my screen. Don't know what's the issue that is coming. Okay. I don't know whether, yeah, it looks better, I guess. Yeah. So for CS3OH that is coming out, we can write a similar equation like we have been doing it. So this CS3OH is for reaction 1. So stoichiometric coefficient is -1. All right. So we already know how much is coming in. 1 minus, we know the extent of reaction is 0.9. So it will be 0.1. So let's denote the fraction of mole fraction of methanol as Y. So it will be 0.1 by the total. We got 6.2 moles. Okay. So this ratio is 6.2, 0.016. So if we have to determine in percentage, so it will be 1.6%. All right. Similarly, for oxygen, that is coming out. Okay, so minus half, extent of reaction of 1. So how much is coming in? Do we know? Yes, we know it is 1 mole. 0.9 by 2. 0.55. So yield, not yield, sorry, mole fraction. Point 0.55 divided by 0.88. Okay. So it will be 8.7%. Next, for formaldehyde, now we can use the extent of reaction for reaction 2, no, for reaction 1. So however much was coming in, we I think calculated it previously. Okay, so we calculated the number of moles of formaldehyde that was coming in reaction 2. So if we use the expression for reaction 2, then it will be much more easier. Okay, so it was 0.9 minus 0.15. 0.9 minus 0.75. So the mole fraction will be 0.75 by 6.2. 0.12, close to 12%. Next, formaldehyde is done, water. So if we do for, we have to do for nitrogen as well. So let's try. Nitrogen is easy. However much nitrogen is coming out is going in. It is not reacting, it is not participating in any reaction. So Xi term will not be there. So we already know this. It is 3.76 moles. So the mole fraction for N2 will be 3.76 by 6.2. Now my pencil is working like butter. I should have done that thing previously. It's good. Anyway, so it will be 0.6, so close to 60%. All right. Next, N2 is methanol, oxygen done, formaldehyde done, nitrogen is done. So two other components are remaining. It is water. First, let's do the water. Now we can take for reaction 1, suppose. All right. So we will press Xi1. Now for water, let me quickly recap. Did we calculate anything regarding how much water is coming in? No, right? Mm, yeah, because water that is coming in, we are not adding any water. So it will be zero because it is formed in the product. So zero amount of water is coming in. So going out will be Xi1. So it will be basically zero point 0.9 moles. So mole fraction of water will be 0.9 by 6.2. 0.145 is close to 14%, 14.5%. Are you following? Are you following the steps?
Yes.
Yeah. Yes. Then for CO, it is getting formed in reaction 2. So however much CO, we are not adding any CO, but it is getting formed in reaction 2. So this is again, this part will be 0. So this will be only Xi2. Xi2 is 0.15, right? So 0.15 divided by 6.2. So 0.024, close to 2.4%. Okay. So there you go. We have calculated the composition, individual compositions in percentage for all the species involved in this particular question. All right, D2I. So any doubts in this question?
No.
No? Okay. So this is the another question that I have for you. It is based on the concept of recycle. So only thing that makes this particular type of problem different from the previous mass balance problems is that there is a another stream. So there is a feed stream. This in this figure, if you see, this is your feed that is entering and the product that is coming out. And in recycle problems, you see there is a third stream. This one R is your recycle stream, where you can see that some amount of P is taken out and recycled back, looped back into the feed stream. So there is two mixing points. So if we say at 1 and 2, at point 1 you see that the recycle stream is getting mixed with the feed and you get a separate type of feed, a mixture of these two entering the process. Whereas in point 2 you see the product that is coming out, it is getting bifurcated, it is getting divided into two components. One component is recycled back, another and the other component is collected. So this is the only difference uh, in this type of problems when you compare it with the previous type of problems where there was only feed and the product streams. Okay, so let's do this fun. This is very easy. All right, this is very easy. Like, take only few minutes to do it. So this is the process. This is the process. Okay, and we see F is the feed that is entering at point 1. There is mixing, so there is now a mixed feed G that is entering the process. Some water is going out and the product P is coming out. But at point 2, recycle is happening. So let's do first write the expression, or first we have to consider a basis. So let's consider a basis of 100 kilomoles, right? Or 100 kg. I think that would be good. Yeah, because we have to find the value of R in kgs per 100 kg of fresh feed. So let's take a basis of 100 kg of fresh feed. Here fresh feed is F. Okay. Here fresh feed is F. And G is the feed that is getting mixed with the recycle and then entering the process. So first write overall balance. When I'm saying overall balance, so I'm considering this. F is entering, all right, and P is going out and 50 kg of water is going out. So instead of writing F, we can write it as 100. So this tells us P, the product, is 50 kgs. Okay. Now, if you look at point 1, okay, at point 1, where there is mixing of recycle feed and the fresh feed, if you do a mass balance there, what do you see? 100 kgs of feed is entering and recycle feed R is entering. What is going out? G is going out or entering the process. This R is entering and F is entering, and what is coming out? G is coming out. So this is an expression that involves R. If you do a balance equation for the component KCl, so you see the KCl and the water percentages are given here. So if you do it for the KCl, you see 30% of fresh feed is KCl, and in the recycle feed there is 50% of KCl. So 0.5 into R, and stream that is entering G, it has 40% of KCl. So now we have two equations and two unknowns, R and G. We can now solve the or get the values of R and G. So if we substitute the value of G in this particular expression, so this expression turns into a expression containing only one unknown. So let's solve it quickly. Point 1 R 10. So R is 100 kgs. So this is your answer, or you can write there is 100 kg of R per 100 kg of fresh feed. Okay. There you go. Understood? Similarly, G will be, if R is 100 kg, so G will be 200 kg. So we got the value of R, that is arcs, but we also obtain the value of P, product stream, and the value of G, the stream that is entering the process. Any doubts? No? Okay. Moving on, this is another similar question on recycle. So there is a vertical dryer. This is the dryer that is used to dry wheat. The flow of air is counter current to the wheat. So this is how the wheat is entering, and this is how the air is leaving. All right. So these are counter current in nature. The exit air from the dryer is recycled. This is the recycle part. For each 1000 kg of wet wheat fed into the dryer, calculate the input of moist fresh air in kg per hour and the recycle rate in kg per hour. The data on stream composition, note some are mass and others are mole fraction. So this is the table that is given to us, this table that shows the mass or mole fraction of water in each of the streams. So we can try to label the streams for our convenience. Let's say W is the wet wheat stream, dry wheat stream is D, exit air is E, recycle stream is R, fresh air is F, and the point and the air that is entering the process is G. Okay. And here, if you see, for when we talk about gases, we consider in general the mole fractions, whereas when for solids, we consider mass fractions. So the values and decimal values that are given for water, for fresh air, it is given in moles. Exit air is given in moles, and air that is entering is also given in moles. So you have to know this, all right? That is a general practice. When you uh, want to express the quantity of air gaseous components, then people use mole fractions. And when we use solid components like wheat or any other thing, like any particular solid form or liquid form, then we use mass fractions. Okay. So these are mole fractions for fresh air, exit air, and the air entering the dryer. And for the wheat, we are giving the mass fractions. So that is why they have written this particular statement to remind us of that fact. Okay. So, but all the calculations has to be done in the same units. You have to consider either all mass fractions or all mole fractions. You cannot mix match the units. Okay. So what we'll do first, we will convert all the mole fractions that are given for the air components into mass fractions. So quickly we'll do it. And we'll take a basis of, so we have already done this. If you remember, we have already converted mole fractions to mass fractions previously in one of those questions. So let's consider a basis of 1 mole for doing all the calculations. Fresh air, yes, one more thing. Let me write quickly the values of water and all the components in the figure so that it makes more sense. So wet wheat has two components, wheat and water. So water is 0.2. So wet wheat will be then 1 minus 0.2. that is 0.8. Similarly, for dry wheat, there will be two components, wheat and water. Water is given to us and it is 0.05. So wheat will be 0.95. What else? So the air components are given to us for E, G, and F. Water components and air components given to us, but in mole fractions. So first let me convert into mass fractions and then we'll fill the values here. Okay. So we have to fill the values of mass fractions for air and water. Here also air and water. Okay. For fresh air, there is air and water. We are given in mole fractions, mole fraction. Fresh air contains 0.0123 moles. So if you divide it, so if you subtract it from 1, so air will be 0.9877 mole fraction. The molecular weight of air and water that we consider is 29 and 18. Okay. So what will be the mass then? 0.29, sorry, 0.9877 into 29. So 28.6433. Similarly, you can take a unit as either kg per mole or gram. Let's say it is gram per mole. So mass that you're getting will be in grams. So you have to think about the units as well and make sure that there is no mismatch in it. Similarly, 18 into 0.0123 will be 0.2214. So mass fraction will be, what will be the mass fraction? You know, it will be sum first individuals and then sum. Let's do the sum here quickly. 286433 plus 0.2214. Sum is 28.8647. So I'll not write the steps. I guess you are able to understand what steps I'm following. I'll just quickly calculate. 0.992, 0.2214. 8. So if you add this, you will get 1. So you have done correctly. Similarly, for exit air, it has two components. Exit air contains water, 0.263 moles. So the remaining will be your air. Point 0.263. 0.737. The same thing, 29 and 18, it will remain same. What will be the mass? (21,373), and for water it will be 4.734. So then the mass fraction. Before that, let me calculate. (26.107). So the air mass fraction is 0. No, now it's correct. 0.819. So there you go for exit air. We have calculated the mass fractions. Now air entering the dryer. It contains 0.066 mole fraction of water and rest is air. Molecular weights will remain same. What are the mass of each component? (27.09) for air. For water, it is 1.188. We take summation. (28.28). So mass fractions is 7.09. 0.958. 0.42. 0.042. So this will be 1. So these are the mass fractions and of air and water in the 3 streams. Let me fill these values in a diagram for the sake of completeness, so that it will be very useful later on when we do the remaining steps. Okay, so we have all the values, but we have to calculate the input of moist fresh air, means F, and the recycle rate R. So again, this will be a mass balance equation we have to write. So if you write an overall balance, means, now before we do that, let's consider a basis. So what basis we must take? 1000 kg of wet wheat is fed. That is our basis. 1000 kg of wet wheat. So overall balance in this case will be 1000 kg of wet wheat is entering. What is entering? F is entering fresh air.
Screen is not.
Yes, you are not able to see my screen.
Yeah.
Let me reshare, okay? Are you able to see my screen now?
Yeah. Now.
Now it's okay? Okay. So these wet wheat is entering and fresh air is entering. If you see the arrows, what is going out? Exit air and dry wheat. E and D is going out. If you do a balance for the wheat, you see 0.8 into 1000 in fresh air. There is no wheat. In exit air also there is no wheat, but in dried component there is 95% wheat. So 0.9 into D. So we can then calculate the value of D. It will be 800 by 0.95, 842.1 kgs. That is the value of feed. That is the value of dried wheat that is going out. Similarly, what is we can do? We can do a component balance for water. Water balance. So you see water is coming in the wet wheat. It is 20% or 2.2 thousand. In fresh air, how much is the mass fraction that is going in as water? 0.008 of F. Then E, exit air, has 0.18 mass fraction of water, and in dried wheat there is 0.05. So D we already know. So rather than writing D, we can write 842.1 to 0.05. Okay. So we have two unknowns, F and E here. So we can't solve it yet. Let's do a balance for air. So in the wheat, there is no air. So 0 into 1000. The air is coming in from this. So 0.992 F to 0.992. In exit air, there is 0.819 and D0. So we have relation between, so we have two equations and two unknowns, F and E. So if we solve these expressions, what we get, so let me write as 1 and 2 for clarity. From 2, we get F is equals to, or E is equals to F into 0.992 divided by 0.819. So F into 1.211. Okay. If we substitute this value of E in 1, substitute 200 plus 0.008 F, 0.181 842. Forty-two point 105. So now we can calculate the value of F. Just few more steps and we are done.
Not getting your voice.
Yes, I'm actually doing the calculations. So, but you can see my screen. I'm writing all the stuff that I'm
Yeah,
doing.
yes.
Yeah.
Okay.
Yeah. Just so F that we got is 748.3. Yeah. It is the F or the
Okay.
fresh moist air is going in. So E exit air will be then 906.19. Okay, so we did this part, and we still have to calculate the value of R. So for that, let's let's consider this point, the mixing point where the fresh air and the recycled air is getting mixed and G is entering the dryer. So at mixing point, if we do a material balance, a total balance first, F plus R equals to G. And we already know the value of F. G and R both are unknown for us, right? F is 748.3. Now we have to do component balance. So let's first do component balance for air. So if we write an expression, we already have all the information with us. We don't know yet how much air and water is there in the recycle feed. So how do we find that out? There is also no information about the recycle percent or the exit air, something like that. Mm. If we don't know that, then we cannot solve this question ahead. Okay. Let me save this question. Let me save this question. If I've missed something, so I've taken this question, which was part of the previous year assignment. Let me quickly have a look at the question in that document. So they have considered, okay, okay, I think I missed something. So I missed something in typing. So in recycle air, there is water, 0.958 mass fraction of water, and then air will be 1 minus 0.958, so it will be 0.042. This information they have considered in their previous question. Okay, so this was I missed out to write. So now that we know this, Let's continue with writing what we were writing. 0.042. No, wait. Sorry, these values are again incorrect. Here, recycle air is, air contains okay. No, no, sorry. Seems like I'm stuck. How did they? Okay, okay, okay. Yes, I got it. So we have to consider the fact that the composition, we don't, the composition of recycled air is same as the composition that is exiting. See this diagram. So recycled air is what? Is some part of the exit air, right? So we know the composition of exit air. So the composition of exit air and the composition of the recycled air will be same. Okay. So we have to consider this particular point. Then we can do it. Okay. So air balance will be then your fresh air contains 0.992 of recycled air will contain 0.819 of air, and G, which is containing 0.98. 958. Okay. Similarly, for water balance, your fresh air contains 0.08. Your recycled air contains 0.181, which is the same composition of the exit air as well. And the air that is entering the dryer contains 0.42. So this is the reactions. There are two unknowns, so two expressions, right? So if we have this expression with us as well. So if we take any of these, if we have three expressions and we can do the solving, let's consider the first one. R we don't know. We have to solve for R. 0.958. So let's solve for R. Is there any doubts? Hmm? Are you getting? I highly encourage you to do the problem on your own. Okay, if you're not comfortable doing it right now, please do it afterwards. Because if you don't practice these type of problems, then it would look very difficult for you. Okay, so you must practice. If you have registered for the certification exam, then it is not like at your wish, but you have to practice. It is a mandatory thing. Okay, more you practice, the better you will get at this subject. Is it clear?
Yeah.
Hmm? So R, or the recycle rate, is 182.9 kgs. Okay, so there you go. The value of R we got, and as well as we can calculate the value of G as well. So it will be 931.2 kgs. So overall, we have calculated almost all the values that are unknown for this particular question. I hope there should not be any doubt. Um, I was asking that will you be willing to stay for a few more minutes or one more question? Or would you like me to end today's session and continue in the next one?
We will continue in the next session.
Oh, okay, okay. So, basically, then the next session, if you see the week's content, they are just revising the material balance thing, like review one, review two, the three, four question, three, four videos. So the same thing I'll do. In the next week, I'll try to come up with uh, questions from different topics, few more topics, uh, on the same material balance questions. Like if you have a difficulty point in for a particular topic, you can let me know now so that I can focus more on that particular topic. Otherwise, what I'll try, like some questions on maybe single unit, multiple unit with reactions, recycle, and then we can also discuss few biochemical reaction based problems, like which uses um, Michael-Menten's equation or Monod's equation. So this is the plan, and a few basic questions as well. So do you think, do you feel like you are not able to understand a particular topic in the material balance topic that has been discussed for so far?
Oh, not like that. But I will.
No. Yeah. Are you
I
able
will.
to solve questions that contains reactions? Are you able to solve those types of questions?
Yeah.
Yeah. Okay. So, all right. So if there is no particular request from your side, I'll try to basically solve at least one question from the different topics that has been covered so far in the material balance topic in the next week. All right. So thank you for joining. I'll see you next week. Yeah. Bye.
Okay, thank you.